In this video, we're going to be talking about exponential functions. We're going to begin by determining whether the table represents a linear or an exponential function, and talk about how come, or rather why we know that. First thing we're going to do with each table is we're going to check and see the difference from our x's. So here we have a plus 1, a plus 1, and a plus 1. So they're changing by 1 each time. From 8 to 4, we are going down by 4, and then we're going down by 2, and then down by 1. So notice here that as we see this, we see that it's not a set number. There was always minus 4, minus 4, minus 4. So this is going to tell us that it's not linear. So we're going to look at it another way, since we're not adding or subtracting the same number, but rather, how else can I get from 8 to 4? Well, what if I divided by 2? From 4 to 2, I could divide by 2. And from 2 to 1, I could divide by 2. Or we call that multiplying by 1/2. At any rate, they're all the same. We're dividing by 2 for each time. So here, this is what's going to let us know that this is going to be an exponential function. So instead of having a constant difference, here we're going to have a constant ratio. Remember how I talked about dividing by 2 is the same thing as multiplying by 1/2? So here's where we would say our constant ratio was 1/2. Because when we talk about constant ratios, we talk about them in terms of multiplication. So it's okay here that we wrote divide by 2, which helps us to decide like, hey, this is going to be exponential. But when we write it, we need to write it in multiplication terms, which would be multiplying by 1/2. Let's take a look at our next example. Here, we can go from 1 to 2 by adding 1, from 2 to 3 by adding 1, and 3 to 4 by adding 1. To get from 3 to 7, we can add 4. To get from 7 to 11, we also add 4, and from 11 to 15, we add 4. So here we have a constant difference, and this is going to make it a linear function because we have a constant difference. And our constant's different, or our constant rate is going to be a rate of 4. Because we always talk about our constant rates in terms of addition. Let's take a look at number 3 and number 4. I'm going to have you do these ones on your own. So go ahead and push pause and do 3 and 4, and then when you're done, push play, and let's see if you were right. So for number 3, we see that the change as we go from each of these numbers is a plus 1. Our change from 12 to 9 is moving down 3, 9 to 6 is down 3, and 6 to 3 is down 3. So here we see a constant rate. So that tells us that we have a linear function with a constant rate of -3. On number 4, to get from -1 to 0, we're adding 1, and from 0 to 1, we're adding 1, and from 1 to 2, we're adding 1. And as we look at the change to get from 0.125 to 0.5, and then from 0.5 to 2, we can see that those aren't going to be the same number. So what we want to do is, what do we either multiply or divide 0.125 by to get to 0.5? Now that can be a little overwhelming sometimes. So it might be helpful to start with, how do we get from 2 to 4? And there we multiply by 4. So from that we can check and see, gosh, if I were to multiply 0.5 by 4, would I get a 2? And the answer is yes. And if I multiply 0.125 by 4, I will also get a 0.5. So that tells us that we have an exponential function because we have a constant ratio of 4. Let's practice evaluating functions. So in this 5th example, we have y equals 3 raised to the x when x equals 5. It's pretty simple. We're just going to take that x equals 5 and replace the x with the number 5. So here we'll have y equals 3 raised to the 5th power. Now what that means is 3 times 3 times 3 times 3 times 3. but we write 3 to the 5th power to make that a little bit less cumbersome to write. So when we multiply 3 to the 5th, and we can plug that into our calculators as 3 raised to the 5th power, or 3 times 3 times 3 times 3 times 3, although 3 to the 5th power is a little bit more time appropriate and will save you time, so it's very time efficient. So 3 to the 5th power will tell us that y is going to be 243. So for number 6, we're going to be replacing this x with the number 3 because we're told that x equals 3. So we're going to have y equals 1/4 raised to the 3rd power. So we can plug that into our calculator, or we can even distribute the 3 to our numerator and denominator and work those out separately. But if we go ahead and plug that in to our calculator, we're going to come out with a value of 1/64. And that's going to be our solution. So I want you to do number 7 on your own. So go ahead and push pause. When you're done, push play, and let's see if you were right. So for number 4, we're going to be replacing our x in the exponent with the number 4, since we were told that x equals 4. So here we'll have y equals 3 times 4 raised to the 4th power. So we can plug that whole thing into our calculator if we want, but I really want to point out that this 4 to the 4th power, that's its own thing. Once we get that answer, then we can multiply that by 3. So if you plug it into the calculator, make sure that you're using parentheses around your 4 or you won't get the correct answer. So here we're going to have an answer of y equals 768, and that's going to be our solution. Next, I want to talk about some of the properties of our parent functions. So here we have the function f of x equals a raised to the x, where a is greater than 0 but not equal to 1, and x is any real number. So notice here I have two. I have one where our x is positive and one where our x is negative. Notice that each one has a small side and then goes up or up to a small side. Either way you look at it, it's going from small to large or large to small. Each graph is going to have the point 0, 1 located on it, as we see here. It's also going to have the point, if it's positive, 1, a, and if it's negative, a negative exponent, it'll be -1, -a. There's also another point that we will have where we will have -1, 1 over a, and likewise here we will have 1, 1 over a. And using those points allows us some ease as we sketch and transform our exponential functions by hand. And that takes us into the transformations of exponential functions. And what does that look like with our equation? So our functions can shift left, right, up, down, they can stretch, they can shrink, they can reflect, and that's located here, kind of like a little hint guide, if you will, where our negative out in the front talks about reflecting across the x-axis. So something going from the top to the bottom. Our a in the front talks about vertical stretches and shrinks. If our number is larger than 1, it'll be a stretch, and if our number is between 0 and 1, it will be a shrink. Our b is our base, so that's not really going to change or be a big deal. Our negative sign in the exponent will reflect across the y-axis, which is what we saw here with our shift and our twist. The m value will represent a horizontal stretch or shrink. This one's kind of backwards, so if our number is between 0 and 1, it'll be a stretch, and if it's greater than 1, it'll be a shrink. The h will represent moving left or right. Left if we see a plus sign in here, and to the right if we see a minus sign. It's helpful to know that anything that's inside the parentheses is probably going to be lying to us. It's going to do the opposite of what we would think. Notice that the reflection isn't across the x-axis but the y-axis. And what we think is a stretch is actually a shrink, and vice versa. Now our k value in the back is going to represent the graph going up or down. And up if we see a plus sign, and a down if we see a minus sign. So what does that look like when the equation is actually written? Let's take a look at that. So here we have some examples. This is called function notation here, where we see our h's and k's and a's and m's written with our f of x. But I think our examples are going to be the piece that helps us the most. So when we're talking about a horizontal translation, meaning that it shifts our graph either to the left or to the right, you're going to see that again we have a minus sign for the right and a plus sign for the left. When we're discussing or looking for shifts up and down, notice our k value is a plus for up and a minus for down. And it's in the back. It's not in the exponent like our h was, like our ups and our lefts and rights were. When we're talking about reflections over our x-axis and our y-axis, we're going to see that when the negative is in the exponent, that's going to make it the y-axis that we reflect over. And when our negative is not in the exponent, we're going to be reflecting across our x-axis. When we're talking about horizontal stretch and shrinks, we're going to be moving away from the y-axis. And those are going to be occurring in the exponent as we see here. And so notice that when I see a 2, it's shrinking by a half. And when I see a half, it's going to be stretching by a 2. So it's kind of the reciprocal of what we see, which is a little bit different from our vertical stretch and shrink, which occurs as moving away or from the x-axis. Here, these numbers occur not in our exponent, but in the front. Notice that when we see a 3, we're in fact stretching by a 3. And when we see a 1/4, we're in fact shrinking by a 1/4. And these can help us decipher what type of transformations we'll have based on our function.